This is problem number 1 on test 3. And the problem introduces a current with 2 different wires. L1, the first wire, has twice the radius of L2, and then there's 2 resistors and 2 batteries. So part A says label the conventional current. And we know that conventional current is going to go towards the negative side of the battery, and it will be the same in both wires. So I will be in this direction here, and I will be in this direction here. Oops. Okay, part B says to write down all of the possible loop rules or energy conservation equations, and next to write down all of the node or conservation of charge rules for both of the nodes. So we'll start with the loop rules. And there's 3 of them. So 2 EMF, which is the voltage supplied by the batteries, it's our total amount of voltage, minus E1 L1 voltage due to the first wire, minus E2 L2 voltage due to the second wire, minus IL times RL to find the voltage due to the resistors. And all of this is going to equal 0. The other one that you can write looks very similar to this, except for at the end, instead of ILRL, you'll have IRRR, because the next one is IRRR equals ILRL. The voltage and the 2 resistors are the same. Next are the node rules. And the conventional current, already said, is the same in both, so that's the first rule, that I1 is equal to I2. And the second is I2, where it branches off here, is going to be equal to the current in the left resistor added to the current in the right resistor. And these equations will be used in the rest of the problem. Part C asked, what is delta V in wire 1? And our method for solving this problem is going to be to isolate E1, because by doing this we know that delta V equals E1 times L, and we know the L, so if we can get E1 we can get the voltage. So we'll start by writing our first loop rule, rearranged a little bit to isolate the E. So E1 L1 equals 2 EMF minus IL RL minus E2 L2. And from the node rules, we know I2 equals IL plus IR, and the IL RL equals IR RR, and because of this, rearranging that to get IR, we have IR equals IL RL over RR. I2, we know the formula for that, so we're going to rewrite that as Q N times mu A2 E2 equals IL, and then we're going to substitute IR from over here. Okay. Then we're going to pull out the IL just to make it look a little bit better and easier to work with. And getting IL by itself, we have this term. Okay, and remember our goal still is to isolate E1, and we'll go back to our loop conservation. And where ILRL was previously, we're going to be plugging in this for IL. This problem is really all about substitution. Minus E2L2. Okay, flip the page. Just simplifying that, we're going to get E1 L1 equals 2 EMF E2 minus E2 times QNU A2 So simplified, this is what we have so far. The next rule we're going to use is that I1 equals I2. We can create a ratio here of the conventional currents. Notice the only thing that's different here is the areas. So E2 is going to equal A1 over A2 times E1. Plug that in to our problem here. So next what we'll do to simplify is pull out the E1 and then move it over since we're trying to isolate it. We're starting to get a little bit smaller equation. Okay, so finally we have isolated E1, and to find the voltage all you have to do is multiply by L1, so we'll plug that in there. And also what we'll do, since we know the radius of the second wire is half the radius of the first wire, that this term will be reduced to 4. So our final answer is voltage equals L1 in the numerator, and then the 4 plugged in for the area ratio. And that is our final voltage. Almost done. Part D asks what is the E in wire 2. So this will be really easy to do because we've already identified this relationship. Or since A1 over A2 is 4, we can just write that E2 equals 4 E1. So E2 is just going to be our answer we previously found, just multiplied by 4. And finally, part E asks to determine the current in the resistor on the right, RR. So we're going to use our relationships. IR equals IL times RL over RR, which we determined that in part C. And then IL equals I2 minus IR. That's just the charge node rule rearranged. Therefore, I2 times RL over RR minus IR over R. Just pulling out and simplifying, we'll get IR times 1. Okay. And then dividing to get, since we're trying to isolate IR, we've already found I2, so we're going to plug that in next. So IR equals this. And then our last plug-in is, since we found in the previous problem E2, we'll plug in for E2. And that is your final answer. Thank you.